Okay guys, in this video we are going to start the lecture series on Chapter 7, which covers different types of chemical bonding, and then towards the end of the chapter we'll talk about different molecular geometries. This video is going to cover the ionic bonding section. Okay, and so we are going to talk a little bit more about cations and anions and the types of compounds that you get, the ionic compounds, and then we'll also look at electronic configurations of metals and nonmetals when they form ions. So first off, an ionic bond between cations and anions is formed through the electrostatic interactions, the attraction between oppositely charged particles. So these are also called Coulomb interactions. Coulomb was a physicist that studied the interactions between objects that have different charges. And so the main rule is that opposites attract. When you form an ionic compound, as we learned previously, metals and nonmetals, when they form compounds, they tend to be ionic compounds. And the reason for that is because metals have relatively low ionization energies, which means it's easy to pull electrons off of a metal atom, and so they typically form cations. Whereas nonmetals, they tend to have large negative electron affinities, which means it's relatively easy to take a nonmetal and have it form an anion, that is, to add an electron to the nonmetal atom. And when you get metal cations and nonmetal anions together in a compound, we call it an ionic compound. Again, the interactions between the cations are these electrostatic Coulomb interactions, and they are relatively strong. And that's what holds the ions together in a crystal. And because they're so strong, ionic compounds tend to have very high melting points. For example, sodium chloride, common table salt, has a melting point of around 800 degrees Celsius. And so that's what it's those strong interactions, those strong Coulomb interactions between the ions that makes it very difficult to melt an ionic compound. It's also what makes them brittle. So when you hit an ionic compound with a hammer, it typically shatters into multiple crystals rather than being deformed like in a metal. When you take an ionic compound and dissolve it in water, or if you heat it up high enough to get it molten, the ions then become mobile, and then the ionic compound can conduct electricity. Ordinarily, the ionic crystals, they are not conductors, they are insulators. So these properties are due to the type of bonding that occurs between the ions, and we call that an ionic bond. Here is an example, a picture example of a crystalline structure. This one's from sodium chloride. It's the structure of the ions within the crystal is due to these interactions between the ions, the electrostatic interactions. And so you tend to see a cation, for example, a sodium ion here. You'll see that it's completely surrounded by chloride anions. So the positive charge is completely surrounded by negative charges, and then you can look at it the other way. The chlorine is completely surrounded by the positive charges. Okay, and so this maximizes the attractive interactions between the ions. In the last part of this video, which will take us a few slides, and the example problems that follow, we're going to be looking at the electronic configuration of different ions. And the configurations that we see in ions, they tend to match or be isoelectronic with a noble gas electronic configuration, or at the very least what we call a pseudo-noble gas configuration, where you have a filled subshell. So there tends to be something very special about having a completely filled shell of electrons, right? Which is what the noble gas atoms have. And when when you see cations and anions forming, the most stable of the ions, they have the same number of electrons. That is, they have the same electronic configuration as a noble gas atom. And so typically the main group metals, they tend to form either a plus G electronic configuration, where G is the group number from corresponding to that particular atom, or it's G minus 2. And so we'll look at some examples of that. When you form an anion, it tends to be the North American group number -8, and so you wind up with a negative charge for the nonmetals, and this typically tends to be what the charge is. Your metalloids, and we can also lump carbon into this. They typically, we don't see them as ions. It's not that they can't be. It's just that that's not what you tend to find in nature. And for transition metals, you'll recall that the transition metals have a partially filled D subshell and a full S shell. That is, the neutral atoms, they have a completely filled S subshell and then a partially filled D subshell. It turns out that the transition metals tend to lose those S electrons first before losing their D electrons. And so I'm going to show you some examples of that. For polyatomic ions, which are part of ionic compounds as well, one thing I want you to keep in mind is that the polyatomic ions, the anions that we've looked at, you can think of these as molecules that are not held together by ionic interactions, but they're actually covalent bonds, which we'll talk about in the next video. They're molecules that have electrons, additional electrons, or if you're talking about a cation, they are short a couple of electrons. But the polyatomic ion is a molecule that has additional electrons, and because it's charged, it can then form ionic bonds with a metal cation, for example. So in this example, we are going to practice writing electron configurations for ions, and we're going to need our periodic table to do that. And so we'll start with, we'll just do the first one here. Well, we'll probably hop around, but we'll start with nitrogen. So let's start with the ground state electronic configuration of a neutral nitrogen atom. And so nitrogen is going to have a helium core, and then it's going to be 2s2, 2p3, right? So I'm using the Aufbau principle here. I'm filling in the helium core, and then we'll completely fill the 2s subshell, and then we'll have 1, 2, 3 electrons in the 2p subshell. So this is neutral nitrogen. Now what we're going to do to form the nitride electron configuration, we're going to add 3 more electrons, right? And those are going to go into the 2p subshell to give us the ground state for the anion. So again, it's helium core, 2s2, and then it'll be 2p6. This electronic structure is isoelectronic with neon. That is, neon and nitride have the same electron configuration. That's what isoelectronic means. Let's look at calcium, cation. So calcium, its electronic configuration is going to be an argon core, and then it has 3s2, 4s2. Now, when you take off 2 electrons, it's going to remove these 2 electrons. And so we're going to have then a neon core, and then it'll be 3s2, 3p6. Right? So we remove these 2 electrons, then we're going to be isoelectronic with argon, and this would be the electronic configuration for argon. For sulfide, we'll do the neutral atom first. For sulfur, we're going to have the neon core. It's going to be 3s2 and then 3p4. We're going to add 2 electrons, and that's going to completely fill the 3p subshell. So we'll have a 3p6 for the sulfide. Again, that's going to be isoelectronic with argon, the nearest noble gas. Let's go ahead and do the lead 4 and the lead 2. So for lead 4, well, we'll do neutral lead first, and then we'll do the cations. So neutral lead, we're going to have a xenon core, 6s2. Then we're going to completely fill the 4f. We'll have 4f14. And then we're going to completely fill the 5d. So this will be 5d10. And then for lead, we've got 2 6p electrons. 6p2. Now when you go to lead 2, you're going to remove these 2 p electrons. Okay, so those p electrons are going to come out first. Then when we go to lead 4, we're going to remove 2 more electrons. Which electrons are going to come out next? It's actually going to be the s electrons. So your heavier metals, they tend to lose their s electrons before they start losing their d and f electrons. So it's going to be 4f14, 5d10 for lead 4. We'll see something similar in part B. Let's look at iron. Okay, so the electronic configuration for iron is going to have an argon core. Then it's going to be 4s2. And then we've got 1, 2, 3, 4, 5, 6 3d6 for neutral iron. Now when we go to form iron 2, it's going to lose these s electrons first. So the transition metals lose their s electrons before they start losing their d electrons, typically. Then when you go to iron 3+, you're going to wind up with a half-filled d subshell. Right? A d subshell can hold up to 10 electrons. With 5 electrons, it's half-filled. There's something special, something extra stable about filled d subshells and half-filled d subshells. That's why the s electrons come out first. Let's look at the same thing is going to happen with manganese and zinc. Let's do zinc. So we'll do the zinc ion. The zinc atom, neutral, has a completely filled 3d subshell. And so we've got the argon core, 4s2, 3d10. Now, zinc forms a 2+ cation. In fact, that's the only cation that zinc really forms naturally. And so which electrons is it going to lose first? It's actually going to lose the s electrons first, because there's something special, something extra stable about that completely filled d subshell. So this is the electronic configuration for zinc 2, zinc 2+. Okay, so when you go to generate the electronic configuration for ions, cations in particular, involving metals, they lose their s electrons first, especially the transition metals. Let's see what I had next. So here we're being asked to take a look at some electronic configurations for different ions, and we're being asked to to decide which ones would you expect in chemical compounds, and then they want us to state the concept or rule that you use to decide for or against any particular ion. Well, for part A, you see that the atom has lost its d electron. This particular electronic configuration, the d electrons have been pulled out first, and so this is not typically what you see in nature. What you'll see in nature are that the s electrons are lost first. So A is one that we won't see. That's what's wrong with it. Rather, what we will see is what I wrote before. You'll have the argon core, and then you're going to have the 3d6. For B, we have a nitrogen with a 2- charge. Okay, and now nitrogen, when it forms an anion, it usually forms an N3-. So nitride is N3-, not 2-. So already we should be suspicious of this one. When you form the 3-, which we looked at previously, you wind up with a electronic configuration that is isoelectronic with neon. So this is a much more stable electronic configuration than this one here for N2-. And so, you know, N2- is not what we expect to see. What we expect to see is the nitride. Part C, this is exactly what we wrote for zinc 2+ on the previous one. So that is a valid electronic configuration for that ion. We do see that one. Part D, sodium 2+. While this may be the correct electronic configuration for sodium 2+, you're not typically going to see sodium 2+ in nature, because when sodium forms a cation, you wind up with this this structure, this electronic configuration, which is isoelectronic with neon again. Okay, and so this is what you see. This is what we find in nature. We don't find the 2+ for a group 1 cation. The calcium 2+ that we have here, this is a valid electronic configuration. You see that we have this noble gas configuration. So this is isoelectronic with argon. And so that's exactly what we expect for calcium 2+. Well, I'm going to stop this video here, and we will pick up with covalent bonding in the next one.